this is too much, right? I'm pouring the trig identities to you. So, Aaron?
Yeah.
Are you familiar with some of these?
Yeah.
Yeah, that's good. Zephyr? You familiar with all these?
Yeah, I know the half angle ones.
Okay. You've seen some of it, right? Okay. So we can continue. And if you look at this over that will cancel the 2, right? So it becomes this, right? So we'll have sine a over 2 over cosine a over 2, well, which equals tan a over 2, right? So this will give us plus or minus tan a over 2, right? And as a matter of fact, we don't need the plus minus sign, because when a is from 0 to pi, a over 2 is just 0 to pi over 2, which is positive. Okay, it's that positive sign. And when a is from pi to 2 pi, then a over 2 is pi over 2 over to pi. In this case, it's the negative one. So it's just straight tan a over 2. Okay? So we have something from here. So we have arc tan a over, oh, that's not sine a. Sine a over 1 plus cosine a. This equals arctan right? These two things are equal, because we just proved it there. Okay, so remember last time I said, well, whenever we have tan, arctan, x, this just equals to x, right? But when we have arctan, tan, x, and this is not necessarily x, because arctan has the value from negative pi over 2 to pi over 2, right? We're gonna adjust it to make it within the range of negative pi over 2 to pi over 2. So then this is the case when we have that. We have arctan tan a over 2. So then we got to look at where they are. So when we have pi or a is within this range, 0 to pi, then a over 2 is within this range. If this is the case, everything's good, because everything's in the first quadrant, right? It's in quadrant 1. So the argument is just simply a over 2, because we're in quadrant 1, right? Or the angle is a over 2. But when a is in the range from pi to 2 pi, then we have a over 2 is in pi over 2 to pi. So it's in this range, which is quadrant 2. But in quadrant 2, we know that tan a over 2 would be negative, right? That's negative. When it's negative, arctan would have the value from negative pi over 2 to 0, right? So this is arctan. This is arctan. That's the horizontal asymptote. So this curve is it's arctan. So if this value is positive, it's this part, right? So that's when you have 0 to pi over 2. When this value is negative, you have this part. So then your result would be from negative pi over 2 to 0. So this is pi over 2, right? So in this case, when a is in this range, a over 2 is in there, we know it's in the second, is the quadrant 2, so this is negative. When it's negative, we get a value in this from negative pi over 2 to 0. So what do? You take out pi from it, right? Because when you're in quadrant 2, you want to go to quadrant 4. You take out pi from it, it goes into quadrant 4. Minus pi. Okay? A over 2 minus pi would get us into quadrant 4. Okay, I'll repeat this. Now a over 2 is in quadrant 2, right? Because it's pi over 2 to pi. That's quadrant 2. Okay? But arctan will never give you any value in quadrant 2. Never. Okay? It can't. Instead of giving you a value in quadrant 2, it'll give you a value in quadrant 4. So you take the value in quadrant 2 minus pi. It goes into quadrant 4, right? Which is going to be a value between negative pi over 2 to 0. So then in this case, this is not the argument yet, but we're going to get a over 2 minus pi. Okay? I wouldn't say this is the argument, because we understand this value is in this range. This is what arctan can generate, right? It generates values from negative pi over 2 to pi over 2. Okay? So then when we get this value, we want it to be the argument. Well, the argument, we want it to be from 0 to 2 pi, right? So then we just have to add 2 pi to it. It'll become a value that is positive. It's from 0 to 2 pi. So this value, so then we can say argument z, in this case, is a over 2 minus pi plus 2 pi, right? Even though both angles are in quadrant 4, right? In this case, a over 2 minus pi, well, originally it was here, right? It's here. This is where a over 2 is. A over 2 is here. So we take out pi from it, or it goes into quadrant 4. Now it's a negative angle. Well, we want it to be a positive angle. That is from 0 to 2 pi, right? So then you just simply add 2 pi to it. It becomes a positive angle. So you add 2 pi to it. And then we have a over 2 plus pi. That's the argument when a is between pi to 2 pi. Okay? So we can say that case 1, when a is from 0 to pi, we have z equals 2 cosine a over 2. Well, in this case, cosine a over 2 is positive. We don't need the absolute value sine. And then we have cosine a over 2 plus I sine a over 2, right? The argument is a over 2. And in the second case is a from pi to 2 pi. The z equals, well, in this case, cosine a over 2 is negative, but the modulus has to be positive, so we put a negative sign here. And we have the argument as a over 2 plus pi sine a over 2 plus pi. All right? And most of this is done, but one thing is missing. What is missing here? An a equals pi. Okay. A equals pi is not here, it's not here. Well, when a equals pi, it's actually easy, because this is the original expression. When a equals pi, we have cosine pi. Cosine pi is -1. Right? So 1 plus -1 is 0, and sine pi is 0. So in this case, z equals 0. And when z equals 0, it does not have a trig representation. Okay? So this one is special. So as we've seen in Desmos, this whole thing is located on a circle, right? It's all a circle. And as well, we can see clearly that 0 is on it, right? And this is the point where we can't represent as a, like, the trig representation, right? This one, we can't. 0 is the only one exception. Everything else we can, right? And when and because 2 pi is not included, but 0 is included, so it's that whole circle. This is the whole circle, but 0 and 2 pi are not included in it. As you can see that from here, so 0 and 2 pi are not included in this. So if you set the angle as 0 or as 2 pi, then when it's 0, this is cosine 0. Cosine 0 is 1, so this is 2. Sine 0 or 2 pi is 0, so this is 0. Z equals 2. So this is not included, right? This one's not included. So what we can see here is that the whole collection, or the whole set of all the complex numbers in this is on the circle where this point is excluded, right? So this is 2, this is 0. And that's that circle, excluding that point. Okay? So it's a bit complex, right? You would have to be familiar with trig to be able to solve this problem. All right? Aaron, how do you feel about this problem? Hard?
Yeah.
Okay, yeah, it's hard compared with the problems we deal with in public school. This is definitely a hard one.
Yeah.
But if you can solve this one, it'll help you to get very familiar with the trig identities.
Yeah.
It'll be easy for you. The trig identities will be very easy for you, right? You want to stretch yourself. Well, if you just look at the trig identities, well, they don't really mean anything to you. Well, then try this, right? It really stretch you so that you go back to trig. All these things start to make some sense. Now let's challenge another one. Okay. For all complex numbers,